Welcome to this video. This is video number 9 in my series of videos on Georg Cantor's contributions to the founding of the theory of transfinite numbers. In this video we're going to take a look at section 18 from that work, and I'm not going to go through absolutely everything from this section. I'm just going to pick out the main features, but some of the things that I go through I am going to go through in quite some detail, but other things I'm going to pass over fairly briefly. I'm still going to mention them, but I'm going to pass over them fairly briefly. So what we're looking to do here in this section is to bring some meaning to the idea of exponentiation as applied to numbers, ordinal numbers from the first and second number classes. Okay, so what I mean by that is when we've got something like gamma to the power of alpha, as it stands we don't know what this means in general. We know how to add transfinite numbers, we know how to multiply transfinite numbers, but we don't know what this means. We might have an intuitive feeling about what it means, but we need to bring some definite meaning to this, some formal meaning to it. So that's what we're going to be doing in this video. Just to clarify what I mean by numbers from the first and second number classes. The first number class is the class of finite ordinals, so 1, 2, 3, up to but not including omega. Omega is the first transfinite ordinal. And then the second number class is the totality of well-ordered aggregates whose cardinal number is Aleph naught, and this is usually denoted as Z Aleph naught. So any well-ordered aggregate whose cardinal number is Aleph naught will belong to this number class. The theorem that I've got written on the board behind me is Theorem A from this section. So let's just take a look at what that says. So let psi be a variable whose domain consists of the numbers of the first and second number classes including 0. Note that 0 wouldn't ordinarily be included in the first number class. That's why we've got to include it as a kind of separate, we've got to mention it as a separate thing here. Let gamma and delta be two constants belonging to the same domain, so the same domain being this domain of first and numbers of the first and second number classes including 0, and let delta be greater than 0 and gamma be greater than 1. Then there is one wholly determined, one-valued function f of psi of the variable psi such that, and then we've got a series of 4 criteria that we need our function f to satisfy. The first is that f of 0 is equal to delta, delta being this number that we've got here. If psi primed is less than psi prime primed, then f of psi primed is less than f of psi prime primed. In other words, our function is order preserving. C, for every psi we have f of psi plus 1 equals f of psi times gamma. The gamma again being the number that we've got up here, whose value we already know. D, if psi sub nu is any fundamental series with psi equals the limit of psi nu, then f of psi nu is a fundamental series with f of psi equals the limit of f of psi nu. Okay, so I've just put a little underline here because in general we wouldn't necessarily be able to guarantee that if we've got a fundamental series and we apply a function to each term of the fundamental series, that we will get another fundamental series. So this is a very particular feature of our function, that we can from a fundamental series we can apply our function to those terms and get yet another fundamental series. And this is only guaranteed really through this property here, that our function is order preserving. If our function wasn't order preserving, this wouldn't happen. So I just wanted to make the point really that this is not a general result for functions of transfinite numbers. This is only a particular result as applied to particular functions and in particular order preserving functions of transfinite ordinals, transfinite numbers. So there's quite a bit for us to go through here. Some things to understand, in particular, we don't have the function yet. We don't have f of psi yet. There's an existence and a uniqueness aspect to this theorem. We need to show the existence of such a function f. So effectively what we're going to have to do is construct f from the ground up. So we're going to start with the first numbers from the first number class and 0, show that we can define a function in an appropriate way such that our function satisfies all 4 of these criteria, or at least the relevant ones, on the first number class including 0. Then we're going to move on to the numbers of the second number class, and there we've got 2 possibilities. We've got, on the one hand, numbers of the first kind, and on the other hand we've got numbers of the second kind. So we're going to treat these separately, and we're going to show that we can define again our function in an appropriate way on all of the numbers of the first kind from the second number class, such that our function satisfies all of these criteria, or at least the relevant criteria. And then we're going to look at the numbers of the second kind and show the same thing, really, that we can define a function in an appropriate way such that on all of the numbers of the second kind from the second number class, such that our function satisfies all of these criteria. And in this way we cover all of the numbers from the first and second number class combined, including 0, and then it just remains for us to show uniqueness, which is not very difficult to do. But just note that in Cantor's actual proof of this, he doesn't really go through the uniqueness part of the function that we derive or that we construct. He goes through the existence, but not the uniqueness. And what Cantor has a tendency to do sometimes is to say something like, we easily convince ourselves that such and such. And sometimes when you peer behind the curtain, it's not necessarily quite so easy to convince yourself of such and such. It takes a little bit more work than you expected. So I'm going to be going into some of the things I'm going to go through in a bit more detail than Cantor goes through in his book. In particular, the uniqueness of the function that we've got here. I'm going to go through that. So in this video, there's going to be some of my own contributions to Cantor's work here. So that's not me trying to rewrite Cantor or anything like that. It's just me trying to fill in some of the gaps and make it a bit easier to understand what we should be convinced of when he says we easily convince ourselves of such and such. But on that note, let's get started on this theorem. So let's have a look now at how we can define our function as applied to the numbers, the ordinal numbers from the first number class including 0. Remember, we are constructing the function here, so there's no question about how do we know that the function takes this value or that value at this value and that value. It does because we define it to be that way. We define the function to be that way. At our convenience, because we want our function to satisfy certain criteria. And if we define our function in that particular way, then it turns out that it does satisfy the criteria that we want it to satisfy. So what we're going to do then is we're going to write f of 0 equals delta. We're going to define f of 0 to be equal to delta, in other words. Again, there's no question about how do we know that. It is because that's what we make it to be. We've got the 4 criteria A, B, C and D. So that means that we've got A accounted for, effectively. So now let's define f of 1 to be equal to delta gamma. Because then we've got that f of 1 is equal to f of 0 times gamma. Then if we define f of 2 to be equal to delta gamma gamma, this is equal to f of 1 times gamma. Similarly, f of 3 is equal to delta gamma gamma gamma. This is equal to f of 2 times gamma. Again, there's no question here about how do we know that f of 1 equals this and f of 2 equals this. It is because that's what we make it to be. And if we continue in this way, then we can define f of nu plus 1 to be equal to delta gamma gamma with an appropriate number of gammas, which is equal to f of nu times gamma. And we can continue that process indefinitely. So what this means is that we've got criteria C accounted for. Okay, f of nu plus 1, or psi plus 1, is equal to f of psi times gamma. So we've got A and C accounted for. Now we can see as well that f of nu plus 1 is greater than f of nu. Remember that gamma is greater than 1, which is greater than we've got f of 3, greater than f of 2, greater than f of 1, greater than f of 0. So in other words, because we know that obviously 0 is less than 1, is less than 2, is less than 3, is less than nu, is less than nu plus 1, we can see that if we take any two numbers, one smaller than the other, then that will give, and we apply the function to each of these numbers, then we'll get another two terms where that are correspondingly in the same order. We've got an order preserving function. So in other words, we've got B satisfied. And this can be extended as well, indefinitely. And D we don't need to worry about, for the simple reason that in the first number class we don't have any fundamental series to worry about. So D either doesn't apply here or it's trivially satisfied because there are no fundamental series. So let's just put a tick next to it. In other words, our function satisfies all of the criteria that we need it to satisfy. What we just need to check now is the uniqueness on this finite, on these finite ordinals. Dead easy to do. So let's assume there is an eta, which is minimal in value, so it's the smallest value of eta such that f of eta is not equal to, let's say, g of eta, where g is some other function that satisfies the same criteria, satisfies all of these criteria, but it doesn't agree with f at this particular value, and this eta is the smallest value. Remember, we're dealing with totalities of ordinal numbers here, and any totality of ordinal numbers will have a smallest value because it's well ordered. Okay, so if that's the case, if we go to the number before eta, so I'm going to write it as eta sub minus 1 rather than eta minus 1, then this will be equal to g of eta sub minus 1, because remember, eta is the smallest value for which f of eta is not equal to g of eta. So these two must be equal. So I'll just clarify here that eta minus 1 plus 1 is equal to eta. But then if I multiply both sides of this by gamma, then I know that this is equal to f of eta. This is equal to g of eta. How do I know that? Because that's criteria C from our theorem, and f and g both satisfy the criteria of the theorem. Oh, so that means that f of eta must be equal to g of eta. So we've got a contradiction here. What this means is that there is no such eta. There is no value of eta amongst the numbers of the first number class, including 0, for which f of eta is not equal to g of eta. So that means that our function that we've constructed is unique, at least on this first number class, including 0. So let's have a look now what happens when we shift to the second number class. So psi now ranges over some numbers of the second number class. And what we're going to do is we're going to assume that we choose a number alpha from that second number class, but alpha is going to be of the first kind. So what that means, if alpha is of a number of the first kind, then it is the successor of another number. So in other words, there is a number alpha minus 1 such that when we add 1 to it, we get alpha. So in contrast to a number such as omega, there is no number immediately before, let's say, omega. There is no number that I can add 1 to get omega. So omega is a number of the second kind, which is, we're going to come on to that shortly, but numbers of the first kind have an immediate predecessor. You can think about it, say if alpha is our number, you can think about this alpha sub minus 1 as almost literally alpha minus 1, although I'm not going to call it literally alpha minus 1. I'm going to call it alpha sub minus 1. Okay, so alpha is a number of the first kind in the second number class, and we're going to assume that f of psi satisfies the criteria A, B, C and D for all psi less than alpha. So for all of the values effectively up to and including alpha sub minus 1, but not including alpha. So what we're going to do then is, given this information, we're going to show that we can somehow construct a value for f of alpha such that it also satisfies the criteria A, B, C and D. And in this way we effectively extend the range of psi just by 1. But once we go to, we've shown that our function can be satisfied by all values up to and including alpha, then we could go to the next one after that, and then the next one after that, and then the next one after that. And we can cover, in this way, all of the numbers of the first kind in the second number class. We've still got gaps where the numbers of the second kind are. That's what we're going to do next. But at least we've got a huge chunk of numbers out of the way, fortunately. So, okay, we've got our criteria, A, B, C and D, that we need to satisfy. A doesn't really come into it at this stage because we've already defined f of 0. 0 is not a number in the second number class, so it's either not relevant to this argument, or we could just say it's trivially satisfied, something like that. One way or the other, it doesn't make any difference. Okay, so then we're going to look at defining f of alpha to be equal to f of alpha minus 1 times gamma. And again, remember, we are constructing this function f. So it's not a question of how do we know that f of alpha is equal to f of alpha minus 1 gamma. It is because that's what we set it to be. And when we do this, when we construct the value f of alpha to be this, then it turns out that it satisfies all of these criteria, and that's what we're going to show now. So, in other words, we've got C satisfied, because remember, C applies already to all of the numbers less than alpha, but now we've shown that it also applies to alpha as well. So we've got C for all of our numbers up to and including alpha. But we can also see, it's a similar argument to what we had last time. F of alpha is going to be greater than f of alpha sub minus 1. But now, because I know that if psi is less than alpha minus 1, so any number less than alpha minus 1, I know that f of psi is less than f of alpha sub minus 1, and I know that alpha minus 1 is less than alpha, so that is less than f of alpha. So let's get rid of these in the middle now, and I can see that if psi is less than alpha, then f of psi is also going to be less than f of alpha. So my criteria B applies now not only to values up to but not including alpha, it applies to alpha as well. Brilliant. And then D, it doesn't really apply to alpha directly. There may be fundamental series in there amongst the numbers up to alpha, but alpha itself is not, it's not a number of the second kind. So any number of the second kind that is less than alpha is already covered, basically, because we know that the theorem applies, all of the criteria are satisfied by all numbers less than alpha, and that includes the numbers of the first and second kind less than alpha. So D is again kind of trivially satisfied at this stage. We don't really need to consider it. We will consider it in a bit more detail in the next argument. So now just let's have a look at what happens when we've got alpha as a number of the second kind in the second number class. But again, we're going to make the same assumption that f of psi satisfies all of the criteria A, B, C and D for all psi less than alpha. Once more, A is not really relevant at this stage, it's kind of trivially true. Also C we don't really need to worry about, but I'll explain that in a bit as we go on. So if alpha is of the second kind, that means that there must be a fundamental series, alpha sub nu, such that the limit of alpha sub nu is equal to alpha. Okay, so what I'm going to do is I'm going to apply my function to each term of this fundamental series. So what I'm going to get is a load of f alpha nu. Now, because this is a fundamental series, all of the alpha nu are going to be less than alpha for all of the subscripts nu. In other words, our function applies to all of these terms of the fundamental series. That means that the function is order preserving on all of these terms. So if it's order preserving, that means that this is also a fundamental series. So it has a limit. This fundamental series, f alpha nu, has a limit. Well, I'm going to call that limit f of alpha. Yes, f of alpha. Again, there's no question here about how do we know that the limit of this is f of alpha. It is by virtue of the fact that I make it the limit of this f of alpha. That's how I define f of alpha. Remember, at this point, when we started, f was not defined on alpha. I've got to construct an appropriate value for f on alpha such that it fits in appropriately with the theorem that we're wanting to prove, that it satisfies the criteria. So what might happen now is we take a separate fundamental series with the same limit as the first one here. So alpha nu primed. What we've got to check is that from this fundamental series, which is different to this one, but with the same limit, that we still get the same f of alpha. In other words, our value for f at alpha is independent of the fundamental series chosen in the first place. Well, because these fundamental series have the same limits, fundamental series have the same limits if and only if they are coherent. And fundamental series therefore are coherent if and only if they've got the same limits. So we can say that we can say that alpha nu fundamental series is coherent with alpha primed nu, and for the same reasons that when we apply f to each of the alpha nu, the terms of the original fundamental series, we get another fundamental series, f alpha nu. We can do the same here, so we get a fundamental series f of alpha primed nu. Now we need to investigate the limit of this, and it's not difficult to show. I'm not going to go through it in this video, but it's not difficult to show that this fundamental series and this fundamental series are coherent. So we have that f of alpha nu is coherent with f of alpha primed nu. And bearing in mind what I said a couple of minutes ago, fundamental series are coherent if and only if they've got the same limit. That means that the limit of this f of alpha primed nu must be the same as the limit of f alpha nu, which is f of alpha. So what we've shown there is that our value of f at alpha is independent of the choice of fundamental series. And through this we've also shown that D holds for any number of the second kind and in the second number class. So we just need to check the last two criteria, B and C here. C we don't really need to worry about too much because our alpha under consideration is a number of the second kind, which means it doesn't have an immediate predecessor. So to say that f of alpha equals f alpha sub minus 1 gamma, where alpha is a number of the second number kind, is meaningless to say, because this doesn't exist. So we don't really need to consider C. C is either not applicable or it holds trivially in the case under consideration. Any number of the first number kind less than alpha, well, we know that the theorem already holds, because by assumption our theorem holds for all numbers up to but not including alpha. So we don't really need to consider part C. We only really need to consider B. Okay, so let's go back to our alpha nu, our fundamental series, whose limit is alpha. So for a fundamental series whose limit is alpha, what we can say is that alpha nu is less than alpha for all nu, so all finite nu. Also worth bearing in mind that alpha is the next greatest ordinal number after all of the alpha nu. We also know that f alpha nu is a fundamental series, and the limit of f alpha nu we've set as f alpha, and again we can say f alpha nu is less than f alpha for all nu. So what we want to show is that our function preserves order right up to and including alpha. So in other words, we know that for all values less than alpha, our function is order preserving. But now we need to show that if we choose any value alpha prime, say that's less than alpha, that we still get that f alpha primed is less than f alpha. So let's choose alpha primed to be less than alpha. Okay, well under these circumstances then, alpha primed is less than alpha. That means that there must be some numbers between alpha primed and alpha. Because remember, alpha is a number of the second kind, it doesn't have an immediate predecessor, so there must be numbers between alpha primed and alpha. And that means that there must be some terms of this fundamental series that are between alpha primed and alpha. So let's say alpha nu naught, which is also going to be less than alpha. Well, I know that because my theorem applies to all values less than alpha, that f is order preserving for certainly these two values here. But also, through this, I can say that this must be less than f alpha. So therefore, if alpha primed is any number less than alpha, then I can show that f alpha primed is also less than f alpha. In other words, my function is order preserving right up to and including alpha, not just up to but not including alpha. I can go up to alpha as well now. So we've got criterion B accounted for. So let's just give some consideration now to possible exceptional values to our function. So it could be, we have to consider the possibility at least, there could be values amongst the numbers of the second number class in particular where our theorem, our function fails. Now bear in mind that any exceptional values, if we pick these out, they will form an aggregate. So there will be an aggregate of exceptional values where our theorem fails. But this aggregate is kind of a sub-collection of a well-ordered aggregate, which is our aggregate of the numbers of the first number class and the second number class, including 0. So that means that our aggregate of exceptional values is also a well-ordered aggregate, and therefore it must have a least value. So let's say its least value is eta. So eta is the least value for which our theorem fails. For which the theorem fails. So that means that for xi less than eta, we've got that the theorem is valid. So let's assume that eta then is a number of the first kind. Well, we've already shown a few minutes ago that if eta is a number of the first kind and the function is valid up to but not including eta, then we've got a way of consistently extending our range of validity, our range of xi, to actually include eta. So that would be a contradiction. Also, if eta is a number of the second kind, again, we've got a way of actually extending xi right up to include eta. So this would be a contradiction then. So in other words, there is no such eta for which our function fails. Now we just need to check the uniqueness. So we've already checked uniqueness for finite values of xi. So now let's have a think about if xi ranges over the second number class. And again, we've got two cases to consider: if xi is of the first kind or if xi is of the second kind. What we'll assume then is that there is another function g of xi, which satisfies all of the conditions of Theorem A. And also f of xi is the function that we constructed. Now let's assume that for some values, g of xi differs from f of xi. And again, these values where they differ are going to form a well-ordered aggregate. So there's going to be a smallest value. So choose, what shall I use? I'll use eta again, actually, it doesn't make any difference. Let eta be the least value for which f of eta is not equal to g of eta. So now if eta is of the first kind, then that means that eta has an immediate predecessor. But we know that f of eta minus 1 must be equal to g of eta minus 1. So just to clarify here, eta minus 1 plus 1 is equal to eta. That's when we've got a number of when eta is of the first kind. Doesn't apply when eta is of the second kind. So that means that if I multiply both of these on the right by gamma, then I get here f of eta, and this is this in the conditions of the theorem, condition C, and this is g of eta. Well, they must be equal then. So again, this contradicts what our choice of eta. The only conclusion is there is no least value of eta, because there is no such value of eta, at least not in among the numbers of the first kind. Okay, so now let's have a look at what if eta is of the second kind. There's a little bit more to do here. So eta is now of the second kind, and that means that there must be a fundamental series, eta nu, such that the limit of eta nu is equal to eta. But because f and g satisfy all of the conditions of Theorem A, for all values less than, and they're equal for all values less than eta, we end up with two new fundamental series, f eta nu and g eta nu. Each with their own limit. So the limit of f eta nu is going to be f of eta. And the limit of g eta nu is equal to g of eta. But here's the thing. Because of the minimality of eta, f eta nu must be equal to g eta nu for all nu. So in actual fact, this fundamental series here and this fundamental series here are one and the same fundamental series. So the same fundamental series cannot have two different limits. So that means then that f of eta must be equal to g of eta, again contradicting the choice of eta as the least value for which f of eta is not equal to g of eta, a contradiction. The only conclusion is that there is no such value of eta. There is no such value of eta among the numbers of the second kind in the second number class for which f of eta differs from g of eta. So that covers all of the numbers of the second kind, the numbers of the first kind, all of the numbers of the second number class. We've already proved the numbers from the first class, so in other words our function is unique. And that finishes the proof of the theorem. Let's just have a quick look at theorems B and C from this section. So I'm not going to prove these theorems, I'm just going to state them because they are useful, we are going to be using them, but I wanted to get onto the proof of the next theorem, which is Theorem D. So Theorem B is effectively Theorem A in essence, with the exception that rather than speaking of general functions, we've got a particular function here, as we'll see. So if gamma is any constant greater than 1, which belongs to the first or second number class, there is a wholly definite function, gamma to the power of psi such that here is where it kind of differs. Gamma to the power of 0 equals 1. So rather than just having delta, we've actually got gamma to the power of 0 equals 1. Psi primed is less than psi prime primed, then gamma to the power of psi primed is less than gamma to the power of psi prime primed, order preserving. For every psi we have gamma to the power of psi plus 1 equals gamma to the power of psi times gamma. And then if psi sub nu is a fundamental series, then gamma to the power of psi sub nu is also a fundamental series. And if psi equals the limit of psi nu, then f of psi equals the limit of f of psi nu. So this is something that, again, it needs proving. We can't just replace the f of Theorem A with this. It does need to be proved, again, almost from scratch, but the way that you would prove this is basically the same as how we went about proving Theorem A. But here we've got a particular type of function in mind, whereas in Theorem A we just dealt with any possible function. And then we come on to Theorem C. If f of psi is the function of psi, which is characterized in Theorem A, then f of psi is equal to delta gamma to the power of psi. In other words, any function constructed along the lines of Theorem A is of this form. So if this is the only function that satisfies the criteria from Theorem A. Remember, we proved in Theorem A that the function that we constructed that satisfies those criteria is unique. Well, in that way, we can show then that if this satisfies the exact same criteria of Theorem A, then this must be the function that we've constructed. So again, I'm not going to go through the proof, it's a fairly straightforward thing to do. I'm going to move quickly on to Theorem D. Let's have a look now at Theorem D from section 18, which is if alpha and beta are any two numbers of the first or second number class, including 0, then gamma to the power of alpha plus beta equals gamma to the power of alpha times gamma to the power of beta. So this in appearance is clearly some kind of extension, some kind of generalization of the usual laws of indices. So for example, x to the power of a times x to the power of b equals x to the power of a plus b. But here we've got a much more general type of number that we're dealing with. And okay, the way that we're going to go about proving this is we're going to form the function phi psi, which equals gamma to the power of alpha plus psi. And what we're going to do is we're going to show that this function satisfies the conditions of Theorem A, first of all. So also it's worth bearing in mind that there is some resemblance here between the function that we've got here and the function from Theorem B, which was just gamma to the power of psi. We're going to be able to use some of the properties of gamma to the power of psi that were shown in Theorem B. We're going to be able to use those to show that this function here actually satisfies the conditions for Theorem A. Notice that in Theorems A and B, we were actually constructing a function from scratch in both cases. We were actually showing the existence of a function that satisfied those conditions, those relevant conditions. Here we're actually given a function. We're given a function, it already makes sense effectively through Theorem B, but we just need to be assured, because it's not exactly the same function. It's got some similarities that we can draw on, but it is a separate function. We need to show that it does actually satisfy the conditions of Theorem A. So what we're going to do is we're going to split things down as usual into psi finite, or from the first number class, psi from the second number class, and then the two cases, first kind and second kind, and show that this function satisfies the conditions irrespective of what type of number we choose from the first or second number class. So let's say psi is from the first number class. Okay, so in that case, let's have a look at phi naught. Phi naught is equal to gamma alpha plus naught, which is equal to gamma alpha, and this is going to be our delta. Okay, from condition A, that our f of naught is equal to some constant value. Well, it is. Gamma to the power of alpha is a constant value. Alpha is just a constant transfinite number. Okay, and then we've got phi of 1, which is equal to gamma alpha plus 1, which is equal to gamma alpha times gamma, which is equal to phi of 0 times gamma. Now, this step here is Theorem B. Theorem B, part C. So this is what I was talking about, that there is some resemblance here between the functions that we can actually draw on. Although they're not exactly the same function, I can still say from Theorem B that gamma to the power of alpha plus 1 is equal to gamma to the power of alpha times gamma. Similarly, phi of 2 is equal to gamma alpha plus 2, which equals gamma alpha plus 1, which equals gamma alpha plus 1 times gamma. Again, Theorem B, part C, which is equal to phi 1 times gamma. And we can continue this to get phi nu plus 1 equals phi nu times gamma. And we can continue that indefinitely. So in other words, our function satisfies criterion C, criteria A, and criteria C when psi is in the first number class. So we don't need to worry about D because there's no fundamental series for us to consider here. We just need to look at B now. It's easily shown that clearly 0 is less than 1 is less than 2 is less than nu is less than nu plus 1, etc. We've also got that phi of naught is less than phi of 1 is less than phi nu is less than phi nu plus 1. So we've got this order preserving function phi. So these come about because gamma is greater than 1. So clearly phi 1, which is phi 0 times gamma, is going to be greater than phi 0. Phi 2, which is phi 1 times gamma, is greater than phi 1, which in turn is greater than phi 0. And we can continue this, and this is criteria B. So whenever we've got psi in the first number class, we've got all of the conditions satisfied. Theorem A applies. Now we just need to check when psi runs over the second number class. So let's have a look now at the case where psi ranges over the second number class, and what we're going to assume is that there is an eta from the second number class but of the first kind, such that our function phi of psi satisfies the conditions of theorem A for all values up to but not including eta. Okay, so criteria A we don't really need to consider because that applies to the specific case when psi is equal to 0. So let's have a look at C. So what we're going to show is that criteria C is satisfied by phi eta. Okay, so phi eta is going to be equal to gamma to the power of alpha plus eta. But remember that eta is a number of the first kind, so it has an immediate predecessor. So this is going to be equal to gamma alpha plus eta sub minus 1 plus 1, which is equal to gamma, using associativity, alpha plus eta minus 1 plus 1, which is gamma alpha plus eta sub 1 times gamma, that's theorem B part C again, which is equal to phi eta sub minus 1 times gamma. In other words, phi as applied to eta satisfies the condition C from theorem A. So not only is C satisfied up to but not including eta, it's also satisfied by eta itself, so we can go all the way up to eta. Okay, so now we just need to show, we really just need to show part B. So to show part B, what we need to prove is that for any, let's say sigma less than eta, that phi applied to sigma is always going to be less than phi as applied to eta. So let's take sigma, which is less than eta sub minus 1, which is less than eta, of course. Then because my theorem I already know applies to these two values, then I know that phi of sigma is going to be less than phi of eta sub minus 1. But I can see from what I've shown here that because gamma is greater than 1, phi eta, sorry, is going to be greater than phi eta sub minus 1. So therefore, sigma less than eta implies that phi of sigma is less than phi of eta, and that's true for all values of sigma less than eta, including eta sub minus 1, by the way. So that proves B, so we've got the order preserving nature of the function for these numbers of the first kind. For D, criteria D, well, it doesn't really apply to eta itself. There may be fundamental series among the numbers less than eta, but by our assumption, the theorem already applies to all of the numbers less than eta. So, because eta itself is not a number of the second kind, which is the only kinds of numbers really that apply to fundamental series, then D is trivially true. So we've shown that this function satisfies all the criteria of theorem A when psi ranges over the second number class and the numbers of the first kind. So let's have a look now at the numbers of the second kind. Okay, so here we've got eta now is a number of the second number class but of the second kind. Same assumptions in place, that our function is valid, it satisfies the conditions of theorem A up to but not including eta. So as usual, let's take a fundamental series, eta sub nu, such that the limit of eta sub nu is equal to eta. Now earlier, I think it's section 14, somewhere in there we prove that limit of alpha plus eta nu is going to be equal to alpha plus the limit of eta nu, which of course is equal to alpha plus eta. So what I'm going to do is I'm going to call these beta nu, and I'm going to call this thing here beta, in which case I can say that the limit of beta nu is equal to beta. Okay. Now again, we're going to draw on the kind of resemblance really of this function with the function from Theorem B, because then I can say that if this is a fundamental series with limit beta, then gamma to the power of beta nu is also a fundamental series, and its limit is equal to gamma to the power of beta. In other words, the limit nu of gamma to the power of beta nu was alpha plus eta nu is equal to gamma alpha plus eta. So taking a fundamental series that has limits eta, then I can show that the limit, should have written this in actually, limit of phi eta nu is equal to phi eta, which is part D from the criteria. Part C is not really relevant here, again because eta is of the second kind, it's not a number of the first kind. So any number less than eta, which is of the first kind, we know that by assumption the function already satisfies the criteria. Criteria A again applies to the specific case when psi is equal to 0, not applicable here. So all we've got to check now is B, the criteria B, which is not particularly difficult to do. If we might need to clear a little bit of space here. So again, going for our fundamental series here, and if we take eta primed less than eta, then there will be values, because eta doesn't have an immediate predecessor, then eta primed, if it's less than eta, then there must still be some numbers in between eta primed and eta, and those some of those numbers will be amongst the terms of this fundamental series. So what I can do is I can find a term of this fundamental series. In fact, there's an infinite number of terms, but there's one in particular, let's call it eta naught, eta nu naught, which is less than eta. And because these two numbers are both going to be less than eta, I know that my function is order preserved by assumption, is order preserving for these two numbers, and therefore phi eta primed is less than phi eta nu naught. But also, remember that this phi eta nu is a fundamental series, and its limit is phi eta, which means that the phi eta nu are going to be less than the phi etas for all nu, in particular for nu naught. So this is going to be less than phi eta, and therefore for any value eta primed less than eta, we've got phi eta primed is less than phi eta, and that's criterion B. So we've got the whole lot accounted for there. So what we've shown is that this function satisfies the conditions for theorem A in all cases of xi, where the xi ranges over the first number class or the second number class or 0, this function satisfies the conditions from Theorem A. So we're not finished yet. We've still got this to do, and that's going to come next. So now let's complete the proof, and what we're going to need to use here is the result from Theorem C. So the result from Theorem C said that the function f from Theorem A is a function of the form delta gamma to the power of psi. Okay, and delta, if you remember, was equal to f of naught. Now we've shown that our phi here satisfies Theorem A. So we don't have delta equals f of naught, we've got gamma alpha equals phi of naught. But because phi satisfies that Theorem A, then it must be of this form. So in other words, we've got phi of psi is equal to delta, which is gamma alpha, times gamma psi. But we also know that phi psi is equal to gamma alpha plus psi. So that means then that gamma alpha plus psi is equal to gamma alpha gamma psi. And now if I just replace psi with beta, I get gamma alpha plus beta is equal to gamma to the power of alpha times gamma to the power of beta. And that proves the result of the theorem. Theorem E from this section is very similar to Theorem D in many respects, including its proof. If alpha and beta are any two numbers of the first or second number class including 0, then gamma to the power of alpha beta is equal to gamma to the power of alpha all to the power of beta. And this is clearly a generalization of the usual laws of indices that you will learn in school. So x to the power of a times b is equal to x to the power of a all to the power of b, except here we're applying it to transfinite numbers. The proof of what we've got to do first of all is create a function which we'll call psi xi, which is xi to the power of alpha, gamma, beg your pardon, gamma to the power of alpha psi. And just like in Theorem D, we need to show that this particular function satisfies all of the criteria of Theorem A, which I'm not going to go through it again. The proof is basically identical to Theorem D, with just a few minor changes here and there. So we're going to assume that, and we're going to go straight to the final part, which is actually proving this. So turning now to Theorem C, the result from Theorem C, we know that any function, the function f satisfying Theorem A is of the form delta gamma to the power of psi. So here, this is the delta, this is the f of 0, and this gamma is the number that we multiply by, if you think about criteria C, we've got something like f of psi plus 1 is equal to f of psi times gamma. What it turns out in this case is that we've got psi plus 1 is equal to psi gamma to the power of alpha. Okay, so again, I'm not going to go through the proof, and this is valid for appropriate numbers. So our delta here is equal to f of naught, but we don't have f's, we've got psi. So psi of naught in this case is equal to gamma alpha times 0, which is gamma to the power of 0, which by Theorem B, part A, is equal to 1. So in other words, our delta in here is going to be equal to 1. So let's make the appropriate substitutions. So psi of psi is equal to delta, which is 1. Now the gamma here in this context we need to replace with gamma to the power of alpha. So it's going to be gamma to the power of alpha to the power of psi. But we also know that psi is equal to gamma alpha psi. Therefore, gamma alpha psi is equal to gamma to the power of alpha to the power of psi. And now if we replace psi with beta, we get gamma to the power of alpha beta is equal to gamma to the power of alpha to the power of beta, which is exactly what we needed to prove in the theorem. And the final theorem from this section, which really in my opinion is more appropriate for the next section, but it's introduced in section 18 in Cantor's work, is simply if gamma is greater than 1, we have for every value of psi that gamma to the power of psi is greater than or equal to psi. This is going to play a crucial part in the next section, which I'll be doing in the next video that I make in this series. I'm not going to do the proof of this. I think I've done enough proof in this video. But suffice it to say that this is an important result, which we'll be using quite extensively in the next section. So that brings us to an end of the content for this video. So in the next video I'll be moving on to section 19, and if you've watched up to this point, then thank you very much for staying with me, and I'll look forward to seeing you in the next video.